Imagine you own, like, a really booming clothing store.
Oh, nice.
Yeah, you have thousands of transactions happening every single hour. You have hundreds of employees on the payroll across, I don't know, multiple locations.
Right, a massive operation.
Exactly. And countless inventory items are just constantly shifting from the manufacturing warehouse to the stockroom to the sales floor. Now, imagine you need to instantly find out exactly which customers living in Texas bought a specific brand of sweater,
Okay.
and specifically in a size medium between January and March.
That is highly specific.
It is. And you need this information right now because you want to send them a highly targeted discount code to clear out the remaining inventory before the summer season starts.
Makes sense.
So how do you find that out?
Yeah.
If you are relying on paper records or just, scrolling through endless messy spreadsheets, you are completely paralyzed.
Oh, you're dead in the water.
Right. You would be spending days, maybe weeks, trying to correlate sales receipts with customer addresses. And by the time you figured it out, the opportunity would just be gone.
Well, the alternative is having the capability to type a single logical sentence and have that exact list of customers materialize in front of you in like 3 seconds.
Which feels like magic.
It really does.
Yeah.
That is the fundamental difference between guessing and knowing. And in modern business operations, I mean, that difference is everything.
Yeah.
It is the absolute secret weapon for how successful organizations leverage the oceans of data they collect every single day.
Well, on that note, welcome to Managing the Future, the MIS podcast.
Happy to be here.
This deep dive into the source material is designed specially for the Dr. Sam Pack College of Business students at Tarleton State University.
And of course, any working professionals out there who are looking to master the realities of modern business operations.
Exactly. Today's deep dive covers Module 29, which is Introduction to Data Analysis with SQL. And this is based on the text by Richard Tedmon and Casey Bilhelm.
We are getting into the absolute engine room of modern business today.
We really are.
But before we get to the mechanics of how data is queried, we really have to look at the context of why this matters so much right now.
Right.
And that takes us directly back to what we covered previously.
Yeah, in our previous deep dive covering Module 28, Emerging Technologies 2025, we looked at some truly mind-blowing advancements.
We unpacked the Internet of Behaviors, or IOB.
Yes, where continuous data is collected from online activities and IoT devices to understand and actually predict human habits.
It's wild. We also explored digital twin technology.
Self-driving trucks navigating highways with LiDAR.
Right, and even artificial intelligence discovering entirely new pharmaceutical molecules.
Which is just incredible. But while all of those technologies sound incredibly different on the surface, they all share one critical, inescapable foundation.
Data.
Exactly. They generate, they store, and they rely on massive, almost unfathomable oceans of data.
Yeah, I mean, a digital twin of a manufacturing plant is entirely useless if it isn't constantly updating its physical counterparts data in real time.
A self-driving truck is essentially just a giant computer processing geographic and sensor data at lightning speed.
Right. To actually manage the future, you have to know how to organize and ask questions of that data.
And that is exactly where SQL comes in.
It is the bridge between raw, overwhelming data and actual, actionable human insight.
Before we jump in, a quick reminder to you, our listener, please take a second to like, subscribe, follow, share, and comment on this track.
It really helps you stay updated and lets you join the ongoing conversation we're having here about the future of business.
Okay, let's unpack this. We throw the acronym around a lot, but what exactly is SQL?
So SQL stands for Structured Query Language.
Okay.
It is the standardized programming language used to interact with relational database management systems.
Which we often abbreviate as RDBMS, right?
Exactly. When you think of major players out there, Netflix, Amazon, Google, your bank, your university, they are all using SQL.
To manage and manipulate the data stored in their relational database tables.
Spot on. It is basically the universal translator for talking to databases.
Now, any tool this ubiquitous must have a compelling set of pros and cons, right?
Definitely.
I know one major benefit is its relatively low barrier to entry.
Yeah, the syntax, the grammatical structure of the language is incredibly intuitive.
Because it reads a lot like regular English.
It does. You don't need a master's degree in computer science to understand the basics of asking for data.
The intuitive syntax is a massive advantage.
Beyond that, it is highly compatible across various platforms.
And its querying capabilities are incredibly powerful for complex data analysis.
Oh, absolutely. You can filter, group, and perform complex math on millions of rows of data in milliseconds.
However, we have to acknowledge the drawbacks.
Right, it's not perfect.
While it is intuitive, it is still a programming language. There is a learning curve.
Particularly when you get into advanced queries.
Furthermore, if your database is made up of massive data sets and the underlying architecture isn't optimized properly.
Oh man, SQL's performance can drop drastically.
Right, a poorly written query can stall an entire server.
I've seen it happen. Finally, the implementation can vary slightly across different database systems.
So you might have to adapt your code depending on the specific platform you were using.
Exactly.
That brings up a great question for the listener. Why should a business major, or anyone listening to this who isn't planning to become a full-time back-end software developer, learn this language?
It's a fair question.
I look at it this way. Data is the lifeblood of strategic decision-making. You don't have to be a hardcore programmer to use SQL.
No, not at all.
Understanding its logic allows managers to ask the right questions and understand the true capabilities and limitations of their IT infrastructure.
And, I mean, the career implications are staggering.
Yeah, the demand for this skill cuts across almost every industry.
According to the data, 72% of SQL developers have a bachelor's degree, but it technically isn't even required to break into the field if your skills are sharp enough.
And the compensation really reflects that demand. The salaries are very compelling. For professionals with strong SQL skills, financial services averages around 131,122 tours a year.
Wow.
Yeah. Healthcare comes in around $113,582.
We're talking about human resources, legal services, logistics. They all pay well into the six figures for the ability to extract meaningful answers from raw data.
Let's trace back to where this all came from, because the history really highlights why the system is designed the way it is.
Yeah, the story begins in 1970.
A researcher named Edgar Codd published a groundbreaking paper introducing the concept of relational databases.
He proposed organizing data into simple tables with rows and columns.
Rather than the complex hierarchical navigational databases that were common at the time.
Which seems so obvious to us now because we are all used to spreadsheets.
But at the time, in 1970, that was a revolutionary conceptual leap.
It completely changed the computing landscape.
By 1974, researchers at IBM began working on a project called System R.
Right, which was the first practical software implementation of Codd's relational model.
As part of System R, they developed a querying language called SQL.
Spelled SEQUEL.
Yes, which stood for Structured English Query Language.
Ah, so that is the historical reason why people in the industry still pronounce it SQL today.
Exactly, even though it is just spelled SQL now.
Due to a trademark issue, it was later shortened to just SQL.
Then, in 1979, a company called Relational Software.
Which you might now know as the tech giant Oracle.
Yeah, they saw the potential and offered the first commercial version of a relational database system.
The adoption was so rapid that by 1986, the American National Standards Institute, ANSI, named SQL the official standard language for relational databases.
And in 1987, it became part of the International Organization for Standardization, the ISO.
So it became the global gold standard.
But this is where I think a lot of business students get tricked up.
Oh.
Yeah, I hear a lot of different terms thrown around that sound identical.
Right.
What is the actual difference between SQL, MySQL, and SQL Server?
Well, it is a common point of confusion. SQL is the language itself.
It is the vocabulary and grammar.
Right. MySQL is an open-source relational database management system software that uses the SQL language.
Okay, so it uses the language.
Exactly. It was introduced back in 1995 and is wildly popular for web applications.
And what about SQL Server?
SQL Server, on the other hand, is Microsoft's proprietary RDBMS software.
Ah.
It was designed specifically for Windows-based enterprise systems.
So if SQL is the language of English, MySQL and SQL Server are two different people who both speak English.
Right, but maybe they have slightly different accents and vocabulary.
That makes perfect sense. But let me push back on this entire relational model for a second.
Okay, go for it.
Because we need to talk about NoSQL. I hear that term constantly when people talk about big data, machine learning, and modern tech.
Sure. NoSQL stands for non-relational databases.
Right. It was developed in the late 2000s specifically to handle rapid scalability and large unstructured data sets.
Instead of strict, rigid tables of rows and columns, NoSQL databases house data within much more fluid, single data structures.
Unstructured data is the key term there.
We're talking about social media posts, sensor data from those self-driving trucks we mentioned, or massive volumes of web app telemetry.
There are 4 major types of NoSQL databases we really need to understand.
First, column-oriented databases.
Which organize data by columns rather than rows for extreme efficiency when querying specific data points across massive data sets.
Second, document databases.
These store data in documents containing fluid pairs of fields and values.
These are incredible for customer personalization and handling messy IoT data.
Third, key value databases.
Where every element is stored as a simple key-value pair.
This speed makes them perfect for things like managing online shopping carts during high-traffic events like Black Friday.
And fourth, graph databases.
Where each element is a node, and the database focuses on the webs of connections between them.
Graph databases are heavily used for fraud detection and analyzing complex social networks.
Now, seeing all that power and flexibility, a logical business mind might ask,
if NoSQL is so great for all this large, modern, unstructured data, why hasn't it completely replaced SQL and relational databases?
Right. Why are we still using a tabular model from the 1970s?
I mean, I look at Netflix and Amazon. They are the pioneers of big data.
We live in an unstructured world filled with TikTok videos, tweets, and sensor data.
Forcing everything into a rigid row and column table feels like trying to put the ocean into an ice cube tray.
That's a great analogy. Why wouldn't a modern business just build everything on NoSQL?
Because while NoSQL is incredible for massive volume and flexibility, it generally sacrifices absolute guaranteed consistency.
Let's look at a bank transfer.
Okay.
If you transfer $10,000 from your savings to your checking account, you do not want flexible, unstructured data handling of that transaction.
No, you absolutely do not.
You need highly reliable, perfectly structured relational tables that ensure ACD compliance.
Meaning every single penny is tracked perfectly.
And if the system crashes midway, the transaction either completely succeeds or completely fails without any anomalies.
Relational databases excel at ensuring uncompromising data integrity for transactional systems.
You used NoSQL to analyze the customer social media sentiment.
But you use SQL to process their actual credit card payment.
That distinction is crucial. I like to think about learning SQL like learning how to use the card catalog at a massive infinite library.
Right. You aren't writing the books, and you aren't building the wooden bookshelves.
You are just learning the exact, specific system required to find the one single page you need in a matter of seconds.
Rather than wandering the aisles for a lifetime.
A financial services manager doesn't need to build the database from scratch.
But they do need to understand if a NoSQL graph database is better for detecting credit card fraud rings.
While a traditional SQL database is required for the core ledger.
Understanding that landscape is what separates a visionary manager from someone who is just guessing.
So let's dive deeper into the architecture of that landscape.
Let's talk about database architecture. Tables, keys, and relationships.
What exactly is a relational database model mechanically?
Mechanically, it is a method for structuring data by storing information in distinct tables.
Think of a table as an independent object that stores data about one specific theme.
Within that table, you have rows and columns.
A row represents an entity, right? Like a specific unique customer or a specific individual product.
Yes, a row is often called a record.
And the columns represent the specific attributes of that entity.
So if the row represents a customer named Jane Doe, the columns might be her first name, her last name, her street address, and her phone number.
Now, if a business has a table with 10 million customers, how do we keep all these rows from getting mixed up?
That's the challenge.
What if we have 2 customers named Jane Doe who live in the same city?
This brings us to the concept of primary keys and foreign keys.
Keys are the structural glue holding the entire relational database together.
A primary key is a specific field, a column that uniquely identifies each and every row in a table.
Because it is the ultimate identifier, it has strict rules.
It has to be totally unique, it cannot ever be duplicated, and it cannot be left empty or what we call null.
It functions exactly like a social security number or a vehicle VIN.
You are a row in the government's database, and your SSN is your primary key.
Nobody else has it, and you can't exist in that system without one.
And then you have a foreign key.
Okay, what's
A
that?
foreign key is a column in one table that links to a column of unique data, which is usually the primary key in a completely different table.
This is the mechanism that allows for cross-referencing between tables.
Exactly.
So if I fill out a medical intake form at a hospital, the hospital assigns me a unique patient ID as my primary key.
Right.
But on that form, I have to list my emergency contact. If my emergency contact is also a patient in that system, my medical record might use their patient ID as a foreign key to link my record to theirs.
The foreign key isn't just a label, it's a structural tether.
These tethers establish what we call database relationships.
And there are three main types you will encounter in any business system.
First, one-to-one.
This means one field in a primary table corresponds to exactly one field in a related table.
A real-world example would be a university database where a student ID links to a specific campus parking pass number.
One student gets exactly one pass.
The second type is one-to-many.
In this relationship, the primary table contains one record that connects to one, many, or even zero records in another table.
Imagine that same university database.
One instructor ID in the instructors table can link to many different student records in the advising table.
Because one instructor advises many students.
Exactly. Finally, we have many-to-many relationships.
Multiple records in one table relate to multiple records in another table.
Continuing the university example, multiple student IDs link to multiple course IDs.
Right. A student takes many courses, and a single course contains many students.
The reason a business professional needs to understand this architecture is because proper design prevents catastrophic data mix-ups.
Oh yeah, if a database is designed poorly and relationships aren't enforced, you end up billing the wrong customer.
Or shipping a physical product to an old address, or losing an order entirely because a record was orphaned.
When you understand these relationships, you see how they turn flat, boring spreadsheets into a multidimensional, incredibly powerful web of business intelligence.
Now, we've talked about tables, but when we look at designing the actual blueprint of a database, there are several other vital database objects we have to understand.
Database objects are fundamental elements designed for specific purposes within the system.
We know the table actually stores the raw data.
But then we have something called a VGW.
Right, a VW is a virtual object. It represents the results of a stored query, but it doesn't store data physically itself.
It acts as a customized window into the database.
Exactly.
Let me put myself in the shoes of a skeptical student here.
Okay, let's hear it.
Why would a business ever want a VW instead of a real table? If it doesn't store data, isn't it just pretend data? Why bother setting that up?
It's highly practical for two reasons: security and simplicity.
Okay, let's tackle security first.
Imagine you hire a temporary marketing contractor. You want them to have a list of active customers so they can send out a promotional email campaign.
Right.
If you give them direct access to your primary customers table, they might be able to see encrypted passwords, credit card hashes, or sensitive internal account notes.
That would be a huge liability.
Instead, you create a VW that only selects the customer's first name, last name, and email address.
You grant the contractor access to the VW, not the table.
They get the data they need, and your sensitive data remains perfectly shielded.
That makes total sense. It is a filtered, secure window into the real data.
Yeah.
What are the other key database objects?
You also have an index, which is a specialized data structure that drastically speeds up data retrieval by using pointers.
We will dive much deeper into indexes later because their impact on business performance is massive.
Very true. Then there is a sequence.
A sequence simply generates sequential numeric values automatically.
If you have an e-commerce site, you want every new order to have an order number that is exactly one higher than the last one.
A sequence handles that automatically. So two orders don't accidentally get the same number during a busy sale.
Finally, we have a trigger.
A trigger is a stored procedure that is automatically activated when a particular event occurs in the database.
Triggers are fascinating from a compliance standpoint.
If someone goes into the database and changes a customer shipping address right after an order is placed, a trigger could automatically log that change.
The time it happened and the user who made the change into a separate security audit table.
A simple trigger can literally save a business during a fraud investigation.
All of these objects, the tables, views, indexes, sequences, and triggers, live inside something called a schema.
A database schema is the logical blueprint for how all of this data is organized and connected.
There are three levels of schemas to conceptualize.
The physical schema describes the hardware level, how the data is actually stored in blocks and bytes on the physical disk drives.
The logical schema focuses on the architecture we've been discussing, the design, the tables, the keys, and the relationships.
And the view schema sometimes called the external schema, defines how the end user actually interacts with the database through applications or reporting tools.
Now, to keep all this data clean and ensure the schema doesn't fall apart, the database enforces strict rules called integrity constraints.
Integrity constraints ensure the accuracy, consistency, and validity of the data.
Without them, human error would turn business data into absolute garbage within hours.
We have 4 main constraints that every professional should be aware of.
First, the primary key or entity constraint, which we touched on earlier.
The primary key must be unique and it cannot be null.
The database will physically reject any attempt to save a row without a unique ID.
Second is the referential constraint.
This rule states that a foreign key must correctly reference an existing primary key.
You cannot have a sales order linked to a customer ID of 999 if customer 999 does not exist in the customer table.
The database will block the order from being saved.
Third is the domain constraint.
This means the data entered must follow a defined format or fall within a specific range.
For example, if you have a column for product price, a domain constraint can dictate that the value must be a decimal and it must be greater than 0.
If a tired employee accidentally types a negative price, the constraint catches the error and stops the system from literally paying customers to take your inventory.
And finally, the not NULL constraint.
Which simply dictates that a specific field cannot be left empty.
If you are filling out a shipping form online and the system flashes red because you forgot to enter your zip code, that is a not NULL constraint in action.
The database is refusing to accept the incomplete record because it violates the architectural blueprint.
Which leads us directly into a massive topic: database normalization.
The term sounds like you are just making things normal, but it is actually a highly rigorous process of extreme organizational efficiency.
Normalization is the systematic process of organizing data in a database to reduce redundancy and eliminate anomalies.
Redundancy is storing the exact same piece of data in multiple places.
It wastes expensive server space and slows the entire system down.
Anomalies are structural inconsistencies that cause fatal errors when you try to insert, update, or delete data.
Let's avoid abstract definitions here and walk through a concrete business nightmare to explain this.
Good idea.
Let's say you manage a regional hardware store and you have a giant flat spreadsheet tracking all your sales.
Okay.
The columns are order ID, customer name, customer address, item 1, item 2, item 3, supplier name, and supplier phone number.
That spreadsheet is a ticking time bomb.
Exactly. Let's look at first normal form, or 1NF.
The rule of 1NF is that you must remove repeating groups so each field contains a single atomic value.
In our messy spreadsheet, we have item 1, item 2, and item 3. That is a repeating group.
If a manager asks, "Show me all the orders that included a hammer," you have to write a miserable query searching across 3 different columns.
To achieve 1NF, you have to flatten the data so there's only one item column.
And a customer buying 3 items generates 3 separate rows.
But flattening the data creates a new problem.
Now that the customer has 3 separate rows for one order, their customer name and customer address are repeated 3 times.
This leads us to second normal form, or 2NF.
2NF ensures all non-key attributes are fully dependent on the primary key.
If the customer's address is stored on every single row for every item they buy, and that customer moves to a new house, you have to update their address on dozens or hundreds of rows.
If your system misses even one row, you've created an update anomaly.
The marketing team pulls a list, hits the outdated row, and sends an expensive catalog to the old house.
To fix that and achieve 2NF, you extract the customer details into their own dedicated customers table with a unique customer ID, and you just leave that ID in the sales table.
You update their address in one single place, and every order instantly references the correct updated location.
Now for the final step, third normal form, or 3NF.
3NF removes any values that are not directly dependent on the primary key.
Look back at our spreadsheet. We have a supplier name and a supplier phone number attached to the order.
But the supplier's phone number doesn't depend on the specific customer's order. It depends on the supplier.
That is called a transitive dependency.
If the supplier changes their phone number, you don't want to dig through thousands of customer orders to update it.
You create a separate suppliers table, link it with a foreign key, and achieve 3NF.
By systematically normalizing this data, you ensure that every piece of information, a customer address, a supplier phone number, and item price, only lives in one single place in the entire database.
You update it once, and the entire multidimensional web of data is instantly accurate.
It saves money on server storage and prevents embarrassing, costly customer service errors.
Now that we have this perfectly structured, normalized, redundancy-free database blueprint, the natural question is,
How do we actually put data into it and work with it?
this brings us to the core mechanics of data manipulation and the specific command types.
Every professional needs to know the acronym CRUD. CRUD.
It stands for Create, Read, Update, and Delete.
These are the 4 foundational operations of data manipulation.
Every single app, website, or software a business uses performs CRUD operations on a database.
Think about a CRM system like Salesforce.
When you enter a new lead, you create.
When you open their profile to find their email, you read.
When they get a promotion and you change their job title, you update.
When they ask to be removed from your system, you delete.
SQL executes these CRUD operations using 5 specific categories of commands.
Understanding these categories helps you realize just how granular database control can be.
Category 1 is DDL, Data Definition Language.
This category manages the overarching structure of the database, not the raw data inside it.
The commands here are create, alter, drop, and truncate.
A quick distinction here that saves a lot of heartache. What is the actual difference between drop and truncate?
Using a real estate metaphor, drop is bulldozing the entire house and ripping out the foundation.
The table, the columns, the relationships, and all the data are completely destroyed and removed from the server.
Truncate, on the other hand, is just evicting all the furniture.
It rapidly deletes all the millions of rows of data inside the table, but it leaves the empty structural shell of the table perfectly intact so you can fill it up again tomorrow.
That is a critical difference if you are managing a daily data pipeline.
Category 2 is DML, Data Manipulation Language.
This is where you interact with the actual data itself.
The commands are select, insert, update, and delete.
So if an HR professional realizes they made a typo when entering a new employee's starting salary, they use an update command, which is a DML command, to fix that specific cell of data without altering the table structure.
Moving on to Category 3, we have DCL, Data Control Language.
This category focuses entirely on access and security.
The main commands are grant, to give a specific user permission to perform an action, and revoke, to take that permission away.
This is how the system administrator ensures the summer intern can only read the data and can't accidentally drop the entire global payroll table.
Exactly. Now, Category 4 is where things get really fascinating for business operations.
TCL, Transaction Control Language.
This manages transactions to ensure absolute consistency.
The commands are begin, commit, rollback, and save point.
I love TCL.
Yeah.
The best way to explain TCL is to compare it to playing a massive, high-stakes video game.
Setting a save point in SQL is literally like saving your game right before you walk into a massive boss fight.
Let's say a business needs to run a huge batch update, changing the health insurance codes for 50,000 employees.
You issue a save point. The system starts updating rows, row 1, row 2, row 3.
But when it hits row 49,000, the server network crashes.
You now have a database in a totally inconsistent state where half your employees have the wrong insurance.
Without TCL, untangling that mess would be an absolute nightmare.
But because SQL uses transaction control language, the system recognizes the transaction didn't finish.
You can issue a rollback command.
It instantly reverts the entire database back to that save point, as if the 49,000 changes never even happened.
TCL commands only ever result in total success, a commit, or total failure, a rollback.
There is no halfway.
This underlying math is how global banks prevent money from just disappearing into the ether if a server crashes midway through a multi-million-dollar wire transfer.
It is the invisible safety net of the modern economy.
Finally, the 5th category is DQL, Data Query Language.
This is designed to perform queries to extract information without actually modifying or touching the underlying data.
There's only one command in this category, and it is the mighty select command.
The select command is the workhorse of data analysis, which takes us right into the syntax of speaking the language.
We need to talk about data types, basic queries, and operators.
Let's start with data types.
A common question from beginners is, why does the database care if a number is designated as a number or just a word?
Why can't we just dump text into a column and let the database figure it out?
Because the data type dictates how SQL will interact with the data mathematically.
And more importantly, how much physical storage space it will consume.
You have character strings, like char, which is a fixed length, and varchar, which is a variable length.
You have numeric types, like int for whole integers, float for floating point numbers, and decimal, where you specify the exact number of total digits and how many digits sit after the decimal point.
And you have date time types like date, date time, and timestamp.
The business implications of choosing the wrong data type are massive.
Let's say a business uses a fixed char50 data type to store a standard two-letter U.S. state code, like TX or CA.
Char50 means the database allocates exactly 50 spaces of memory for every single row, no matter what.
So for TX, you are storing 2 letters and 48 blank, invisible spaces.
If you have a table with 1 billion customer records, you are suddenly paying for massive amounts of expensive, premium cloud server storage just to store blank air.
If they'd used a char2, they would save terabytes of space, and the database would run significantly faster.
Let me give you another disaster scenario regarding data types.
Okay, let's hear it.
Let's say you store U.S. zip codes as an INT, an integer data type instead of a varchar text string.
Mathematically, the integer 02134 is just 2134.
The database will automatically drop the leading 0 to save space.
Suddenly, every single customer living in New England where zip codes start with 0 has an invalid 4-digit zip code.
Mail gets lost, packages bounce, and millions of dollars in revenue are delayed.
All because a database architect chose a number type instead of a text type for a field that didn't require mathematical calculation.
That is a phenomenal example of why technical details dictate business reality.
It is also why we use logical naming conventions.
Best practice is to use lowercase letters and underscores, like customer or shipping address.
So the architecture is consistent and instantly readable for anyone writing a query against the database.
Okay, let's actually build a query mentally.
The simplest query requires 2 fundamental keywords.
You must have a select statement telling the database exactly which columns you want to see.
And a from keyword, telling it which specific table to look in.
And in SQL, every query must end with a semicolon to tell the engine the thought is complete.
So select email from employee gets me a massive unorganized list of every email in the company.
But what if you have duplicate emails because someone was entered twice?
You use the distinct keyword right after select to force the database to eliminate duplicates and only return unique values.
And what if you only want to see the emails of employees who work in Texas?
You use the where clause to filter the results based on a condition.
You write select email from employee where state equals TX.
Notice the single quotes around TX. In SQL, text strings must always be enclosed in single quotes, whereas numbers do not.
If you want to see every single column without typing all their names, you can use an asterisk, which acts as a wildcard, meaning all.
Select from employee gives you everything.
But business questions are rarely that simple. A manager usually wants complex, multi-layered filtering.
That is where operators come into play.
We have several families of operators. We have arithmetic operators, the plus sign, minus sign, multiply, divide, and modulus, which is represented by a % sign in the code.
The outline mentions that modulus returns the remainder of a division operation.
Yeah.
It only works on integers.
Right.
I have to admit, when I first read this, I thought it sounded incredibly obscure. Why on earth would a business person ever need to find the remainder of a division in a database?
It sounds like pure academic math, but it is actually an incredibly practical operational tool.
Okay, how so?
Let's say a marketing team wants to run a promotion and identify every 10th customer that made a purchase today for a special giveaway.
You simply run a query using modulus 10 on the order ID number.
Whenever the query calculates a remainder of 0, you have found your 10th, 20th, or 100th customer.
Furthermore, logistics companies use modulus constantly for load balancing.
If you have 1 million incoming packages and 10 shipping containers, you can use a modulus operator on the package tracking number
to instantly and evenly distribute those packages across all 10 containers without complex routing logic.
That is a brilliant application of basic math to solve a massive logistical headache.
What other operators do we have at our disposal?
We have comparison operators, equals, greater than, less than, greater than or equal to, and not equal to.
Interestingly, not equal to is usually written as a less than sign followed immediately by a greater than sign.
And then you have logical operators, ND, where all conditions specified must evaluate to true, or R, where any single condition can be true and not, which reverses the Boolean value of a condition.
Combining these operators is how you generate highly targeted business intelligence.
Let's say a business owner is querying for customers who have spent less than $300 total, and they have not shopped since 2023.
They have to use the correct combination of logical operators, comparison operators, and date types to get an accurate list for a win-back email campaign.
And when you start combining all these operators into a single massive query, you absolutely have to understand operator precedence.
Operator precedence is exactly like the order of operations in basic algebra.
The database engine resolves the query in a very specific, unbreakable order.
Parentheses always go first, then multiplication, division, and modulus.
Then addition and subtraction. Then all the comparison operators.
Finally, the logical operators are resolved in the specific order of not, then AND, then OR.
The danger here is that if a business analyst doesn't know the precedence rules, their query might execute perfectly without throwing an error, but it will return completely wrong data.
They hand a flawed report to the CEO, a multi-million-dollar decision is made, and the foundation was totally compromised.
Mastering the syntax isn't just about not getting errors, it's about guaranteeing the truth of the output.
Moving on to making sense of all this data, we have to talk about aggregation, grouping, and functions.
Raw data is functionally useless to an executive.
A VP of sales does not want to see a spreadsheet with 10,000 individual sales rows.
They want to see a summarized dashboard.
That is where aggregate functions come in.
They take thousands of rows and compress them into a single, meaningful insight.
The most common ones are SUM, to add numerical values up, AVG, to calculate the mathematical average, count, to find the total number of rows, and max and MIN, to find the highest and lowest values in a data set.
But we have to address how these functions handle NEL values.
If a field in the database is entirely empty, does the aggregate function treat it as a zero?
No, and this is a vital distinction that catches people off guard.
NELL means the data is missing, unknown, or undefined. It is a void. It is not the number zero.
A customer who has spent $0 is mathematically different from a customer where their spending history is unknown.
Because of this, all aggregate functions like NEL and AVG ignore NEL values entirely when running their math.
There is one major exception, the count function.
If you run a count on all rows, it will count a row even if it contains an NEL value, because the row itself still physically exists in the table.
Now, when you run these functions, the column name in your query results might look really ugly and technical, like SUM sales amount.
If you are exporting this to a report, you want it to look professional.
You can rename it dynamically using the AS keyword, which is called aliasing.
You can write SUM, sales amount, so total revenue, and the resulting column will have that clean, readable label temporarily without altering the underlying database schema.
Okay, so we can find the total global revenue, but what if the VP wants to see the total revenue per state?
You use the group P by Y statement.
Group P by Y organizes identical data into distinct subsets based on shared attributes.
You could query select state, SEO sales amount, and then add group P by Y state at the end of the query.
The database engine will gather all the Texas sales rows into one bucket, all the California sales into another, and give you a neat, organized list showing the sum for each individual state.
This brings up a common trap.
What's that?
What if I want to group the sales by state, but I only want the report to show me the states where the total sales are greater than $1 million? Can I just use a where clause for that?
No, you cannot. This is a crucial concept regarding the order of operations within SQL.
The where clause filters raw rows before they are grouped or aggregated.
The database hasn't calculated the sum yet, so it can't evaluate if the sum is over $1 million.
To filter group data, you must use the halving clause.
The halving clause filters the data after it has been aggregated by the group by Y statement.
So your query would end with having sales amount 100,000.
A concrete scenario for this. An HR director wants to calculate the average hourly pay rate for employees.
Group by job title, having an average rate less than $25 an hour.
So they can immediately identify which departments need a baseline wage adjustment to maintain equity.
It is an incredibly powerful analytical tool for finding outliers in massive data sets.
What about cleaning up messy data before we analyze it?
Human beings are notoriously terrible at entering data perfectly. People leave caps lock on, they add extra spaces, they misspell things.
SQL has an entire library of character functions designed exactly for data cleaning.
Functions like upper and lower force text strings into all caps or all lowercase to ensure uniformity.
Length tells you exactly how many characters are in a string, which is great for finding invalid phone numbers.
Substr retrieves just a specific targeted part of a string.
And then you have the real lifesavers. Trim, which automatically removes unwanted blank spaces from the beginning or end of a string, and replace, which swaps one specific character string for another.
I cannot emphasize enough how important trim is.
I compare trim and replace to the essential spell check and formatting tools in a word processor.
Imagine a scenario where a sales rep accidentally hits the spacebar after typing a client's ID number.
To the human eye on a screen, ID 123 and ID 123 look identical.
But to a database, there are two completely different values.
A multi-million-dollar revenue report might fail to link that client's purchases because of one invisible space.
Wrapping your queries in a trim function strips that space away and saves the day.
Beyond character functions, SQL also possesses built-in math functions.
ABS calculates the absolute positive value of a number. Round allows you to specify exact decimal lengths for financial reporting.
SquareRT calculates square roots. There is also a highly useful rand function which generates a floating point random number between 0 and 1.
Why would a database need a random number generator?
For statistical sampling.
If an auditor needs to randomly select 100 transactions from a database of 10 million to check for compliance, they can't just pick the first 100 rows.
By using a formula like round 1 plus rand 99, they can instruct the database to randomly select unbiased rows for their audit, ensuring statistical validity.
We have covered so much ground, but we absolutely have to get to the most powerful concepts in SQL.
We are talking joins, subqueries, and indexes.
Let's start with joins. This is the actual magic that makes relational databases superior to flat files.
A join clause is how you combine rows from two or more separate tables based on a related common column between them.
This is the operational mechanism for how you bring together the customer table and the orders table to generate a complete invoice.
Let's visualize this using a Venn diagram and an e-commerce shopping cart.
The left circle is our customers table. The right circle is our shopping carts table.
What are the different flavors of joins?
The most common is the inner join.
Think of this as the overlapping center of the Venn diagram.
An inner join returns only the records that have matching values in both tables.
If you run an inner join on customers and shopping carts, the result will only show you the customers who actually have an active cart. Anyone without a cart is excluded.
But what if the marketing team says, we want a list of every single customer in our database, and if they happen to have an active cart, show us what's in it. If they don't, just leave that part blank.
For that, you use a left join.
A left join returns all records from the left table in this case, all customers, and only the matched records from the right table.
If a customer doesn't have a cart, their name still appears on the list, but the shopping cart columns will simply populate with NULL values.
A right join does the exact opposite, pulling everything from the right table.
And finally, a full join returns all records when there is a match in either the left or the right table, effectively merging the two entirely based on the key.
The next power move is the subquery.
A subquery is essentially a query nested inside another query, always enclosed in parentheses.
They can return a single distinct row or multiple rows, and they are usually utilized within the where, having, or from clauses to drive the logic of the main query.
Give me a real-world scenario where a subquery is the best tool for the job.
Let's say you are an inventory manager.
Okay.
You want to find the names and phone numbers of customers who have purchased a specific luxury item that costs over $5,000, so you can invite them to a VIP event.
You can't just look at the customers table because the price data isn't there.
You could write an outer query, select name, phone from customers where customered in.
And then your subquery in parentheses would be select customer from purchases where sale amount 5,000.
The elegance of that is amazing. The database engine runs the inner subquery first.
It scans the purchases, generates a list of IDs of high rollers, and then feeds that raw list directly to the outer query to extract the names and phone numbers.
It breaks down complex multi-table filtering into logical, readable steps without requiring complex join logic.
It is incredibly efficient for developers to write, read, and maintain over time.
Finally, we have to do a deep dive into indexes.
We mentioned them earlier as a database object, but let's really unpack the mechanics here because they dictate whether an app is lightning fast or unbearably slow.
An index is a specialized background data structure that allows the database engine to find specific data instantly without having to scan the entire table row by row from top to bottom.
It functions using an index key and a pointer that points directly to the physical location of the record on the hard drive.
To create one, you issue a DDL command specifying an index name, the table name, and the key column you want to index.
So if I have a database with 50 columns and indexes make everything so fast, why wouldn't I just index every single column in my entire database?
Because indexes are a massive double-edged sword.
Yes, they speed up data retrieval, the select queries, immensely.
But they take up substantial physical disk space. More critically, they negatively impact performance whenever you're updating, inserting, or deleting data.
Let's break down why that happens. I think of it exactly like the index at the back of a massive 1,000-page textbook.
If you want to look up a specific topic, the index makes it incredibly fast. You just flip to the back, find the word, and it gives you the exact page number.
You don't have to read the whole book.
But if the author decides to add a new chapter or insert a new page right in the middle of the book, they have to go back and completely rewrite and update the entire index to fix all the page numbers.
That analogy perfectly illustrates the concept of update lag.
Every single time a new customer places an order and a new row is inserted into the table, the database must pause and computationally update the underlying index structure to include the new pointer.
If you have 20 indexes on a table, one single insert command triggers 20 separate background update processes.
If you are running a high-volume system like a ticket-selling website on the morning a major concert goes on sale, too many indexes will cause the database to grind to a halt under the weight of its own internal updates.
Indexes are powerful, but they must be used strategically only on columns that are frequently searched or used in join conditions, not just blindly applied to everything.
It is a constant balancing act between read speed and write speed.
It truly is incredible how these underlying invisible mechanics, the relational constraints, the subqueries, the transactional rollbacks, and the B-tree indexes power the entire modern digital economy.
If you understand these concepts, you understand how modern businesses actually function on a fundamental level.
You move from just being a passive end user of technology to someone who understands how to manage, architect, and leverage it for strategic advantage.
Well, to you, our listener, thank you so much for joining us on this incredibly deep dive into the architecture of data.
It has been a pleasure walking through this complex material with you.
Before you go, we want to invite you one last time to like, subscribe, follow, and share this track.
But most importantly, leave a comment.
We have a discussion question for you, and we want to see your analytical answers down below.
Here is the question for today. Think about an app or a local business you interact with every single day.
If you were hired to design their database from scratch, what are 2 specific tables you would create?
What primary and foreign keys would you use to link them?
And finally, what is one critical business question you would use a SQL select statement to answer?
Let us know in the comments.
We really want to thank you for sticking with us through this educational journey. This actually marks the final deep dive of this podcast series.
It has been an incredible run exploring everything from emerging AI to the foundations of relational data.
It truly has.
Yeah.
Please encourage your peers to check out our channel for other related podcasts and video series we've produced.
Keep learning, keep questioning, and keep exploring the systems that run our world.
A quick note on our sources for those following along. Content for today's episode was drawn from Richard Tedman and Casey Wilhelm, ConnectMaster. Management Information Systems, McGraw-Hill, 2026.
And as we sign off, we want to leave you with a final thought to mull over as you build your career.
We spent Module 28 talking about the rapid exponential evolution of AI in machine learning.
As those technologies continue to advance and natural language processing gets better, how might the way we write SQL queries change?
Will we soon reach a point where we just ask an AI chatbot in plain English to write our complex subqueries and joins for us?
Or will understanding this underlying relational logic become even more valuable as a uniquely human, critical thinking skill required to double-check the AI's inevitable hallucinations?
It is the difference between simply driving a car and knowing how to build, tune, and fix the engine.
Something to mull over as you step into managing the future.
Thanks for listening.